Right now, ancient light from the birth of the universe is passing through a hole in space 1 billion light-years wide, and it is arriving at Earth colder than it should be. Scientists discovered this in 2005, and the implications are still unraveling. The Eridanus Supervoid is not empty space between stars. It is a wound in the cosmic web itself, a region where galaxies simply do not exist. This void is so massive it leaves a scar on the oldest light in existence, the cosmic microwave background radiation from the Big Bang. That scar appears as a cold spot 10 degrees across the sky, 70 millionths of a degree colder than surrounding space. Standard physics says this should not happen. Random fluctuations cannot produce something this extreme, yet multiple satellites confirmed it. The void is real, and it is stealing energy from light that has travelled for 13.8 billion years. We will trace the discovery that revealed this cosmic absence, explain how a void can drain energy from photons, and confront what it means that the universe is dominated by holes we barely understand. If you want to see how emptiness reshapes reality, hit that like button and subscribe. Prepare yourselves. We begin. 3 astronomers were staring at a map of the universe when they noticed something impossible. The map showed temperature variations in the cosmic microwave background, the faint afterglow of the Big Bang that fills all of space. Every spot on this map should look roughly the same. Small fluctuations are expected, tiny hot and cold patches representing density variations in the infant universe. But one region was different, dramatically different. The cold spot sat in the constellation Eridanus, covering an area roughly 10 degrees across. That is 20 times the width of the full moon. For cosmic microwave background standards, this is enormous. The temperature deficit was 70 millionths of a degree Kelvin colder than the surrounding sky. That sounds insignificant until you realize the entire cosmic microwave background only varies by about 100 millionths of a degree in total. This single cold spot represented a massive deviation. The Wilkinson Microwave Anisotropy probe discovered it in 2005 during its mission to map the cosmic microwave background with unprecedented precision. The satellite spent years scanning the entire sky, measuring temperature variations that reveal how matter was distributed moments after the Big Bang. Every other feature in the map made sense. The hotspots lined up with regions that would later collapse into galaxy clusters. The cold spots matched future voids. The overall pattern confirmed predictions from Big Bang cosmology with stunning accuracy, except for this one spot. Scientists ran the numbers immediately. They calculated the probability of such a large, cold anomaly appearing by chance from random quantum fluctuations in the early universe. The answer was uncomfortable. Statistical models suggested this kind of feature should appear in only about 2% of universes. Not impossible, but unlikely enough to demand explanation. Some researchers dismissed it as a statistical fluke. The universe is large. Rare things occasionally happen, but others were not convinced. The Planck satellite launched in 2009 with even better instruments and higher resolution. If the cold spot was an artifact, a glitch in the Wilkinson probe's instruments or data processing, Planck would expose it. Instead, Planck confirmed everything. The cold spot was real. Its size and temperature deficit matched the original measurements. Multiple independent analyses using different techniques all reached the same conclusion. The cosmic microwave background contains an anomaly that standard cosmology struggles to explain. Theories emerged immediately. Some physicists proposed exotic explanations. Perhaps the cold spot represented a collision between our universe and another universe in a multiverse. The impact could have left a bruise in space-time, visible as a temperature deficit in the cosmic microwave background. This idea gained brief popularity in the media because it sounded dramatic, but it lacked supporting evidence and required assumptions about multiverse physics that remain entirely speculative. Other researchers suggested the cold spot might be a cosmic texture, a topological defect left over from phase transitions in the early universe. These defects are predicted by some quantum field theories, though none have ever been observed. A texture in the right location could potentially create the observed temperature pattern. But again, the explanation required invoking phenomena we have never detected and might not exist. The simplest explanation was also the most troubling. Maybe the cold spot was just an unlikely statistical fluctuation. The universe rolled the dice and came up with a rare result. We happen to observe it because we can only observe one universe, our own. If this was true, it meant nothing about physics needed revision. It just meant we got unlucky and found an anomaly that tells us nothing useful. Scientists hate this explanation because it is not falsifiable and provides no insight. But there was another possibility that no one initially considered. What if the cold spot was not created in the early universe at all? What if something between us and the cosmic microwave background was affecting the light on its journey to Earth? Light from the cosmic microwave background to reach our telescopes. During that journey, it passes through everything that formed after the Big Bang. Galaxy clusters, filaments, voids. Each structure the light encounters can leave an imprint. This realization changed the investigation completely. Astronomers stopped looking backward at the early universe and started looking sideways at the structures surrounding us today. If something along the line of sight was modifying the cosmic microwave background temperature, it had to be massive. Small structures like individual galaxies or even galaxy clusters cannot create temperature deficits this large. Only something on the scale of hundreds of millions or billions of light years could affect such a huge patch of sky. Scientists began surveying galaxies in the direction of the cold spot. They needed to map the three-dimensional distribution of matter along that entire line of sight. This required measuring distances to thousands of galaxies, determining which ones were relatively nearby and which were billions of light years away. The work was painstaking. Each galaxy needed a spectrum to measure its redshift, which reveals its distance through the expansion of space. The surveys took years. Multiple telescopes contributed data. Researchers compiled catalogues of galaxy positions stretching from the Milky Way outward toward the cold spot and beyond. They built three-dimensional maps showing where galaxies clustered and where they were absent. Slowly a pattern emerged. There were fewer than there should be, not slightly fewer, significantly fewer. The deficit extended across hundreds of millions of light years. It was not a small gap between galaxy clusters. It was a supervoid, a region where the overall density of matter was 20 to 30% below the cosmic average. This underdense region sat roughly 3 billion light years away from Earth, positioned almost perfectly along the line of sight to the cold spot. The discovery had a name within months, the Eridanus Supervoid, named for the constellation where it appears in our sky. Its size was staggering. Depending on how you measured it, the void stretched anywhere from 800 million to 1.8 billion light-years across. This made it one of the largest structures ever observed, and it lined up almost exactly with the cosmic microwave background cold spot. This could not be coincidence. The void had to be responsible for the temperature deficit. But how does a region of space with fewer galaxies make the cosmic microwave background colder? The mechanism was not immediately obvious. Voids are not truly empty. They still contain some galaxies, dark matter, and dark energy. They are just less dense than average. Why would light passing through a less dense region lose energy? The answer required understanding how gravity affects light over cosmological distances and how the expansion of space changes gravitational potentials. The physics was subtle but devastating once you worked through it. The Eridanus Supervoid was not just sitting quietly in space. It was actively draining energy from every photon that passed through it. And this process revealed something fundamental about how voids shape the universe we observe. Galaxy surveys are the most tedious work in astronomy. You point a telescope at a tiny patch of sky and collect light from everything in that region. Most of what you see are galaxies, each one a collection of billions of stars so distant they appear as faint smudges. To learn anything useful, you need more than pictures. You need spectra. A spectrum splits the light into its component wavelengths, revealing which elements are present and how fast the galaxy is moving. The motion is what matters for mapping voids. When a galaxy moves away from us, its light stretches to longer, redder wavelengths. This is redshift, caused by the expansion of space itself. The farther away a galaxy is, the more space has expanded between us and it, and the more its light has been stretched. By measuring redshift, astronomers can calculate distance. This turns a two-dimensional image on the sky into a three-dimensional map of where galaxies actually sit in space. Teams of astronomers spent years measuring redshifts for galaxies in the direction of the Eridanus cold spot. They used multiple surveys, cross-checking data to ensure accuracy. The Sloan Digital Sky Survey contributed observations. The 2-degree field galaxy redshift survey added more. Smaller targeted surveys filled in gaps. Each galaxy became a data point, a position in three-dimensional space marked by its coordinates on the sky and its distance from Earth. When researchers plotted these positions, the structure of the cosmic web revealed itself. Filaments of galaxies stretched across hundreds of millions of light-years, chains of light tracing the densest regions of matter. Where filaments intersected, galaxy clusters formed, bright nodes containing hundreds or thousands of galaxies packed relatively close together. Between the filaments lay darker regions where galaxies were sparse. These were the voids. But one void stood out. Starting about 2.5 billion light-years away and extending outward for another billion light-years, there was a region where galaxy counts dropped significantly. The researchers counted galaxies in this region and compared the number to what they should find in a typical volume of space. The deficit was clear, 20 to 30% fewer galaxies than expected. Some analyses suggested the deficit might be even deeper in the void's core, approaching 40% in the most underdense regions. This was the Eridanus Supervoid. Its boundaries were not sharp. Voids do not have walls. Instead, density gradually decreases as you move from the surrounding filaments toward the void's center, then gradually increases again as you exit the other side. The void's size depended on how you defined its edges. If you measured from the point where density first dropped below average to where it returned to average, the void stretched roughly 1 billion light-years across. If you used a stricter definition, requiring density to be significantly below average, the size was smaller, maybe 800 million light-years. Either way, it was enormous. For comparison, the distance from the Milky Way to the Andromeda Galaxy is 2.5 million light-years. The distance to the Virgo cluster, one of the nearest large galaxy clusters, is about 50 million light-years. The entire local supercluster, the large-scale structure containing our galaxy and thousands of others, spans roughly 500 million light-years. The Eridanus Supervoid dwarfed all of this. It was a hole in space larger than multiple superclusters combined. The void's position was equally important. It sat almost directly along the line of sight to the cosmic microwave background cold spot. Light from the Big Bang, travelling toward Earth from that direction, had to pass through the entire depth of the void. This was not a glancing intersection. The void was positioned such that photons traversed nearly its full diameter before reaching our telescopes. Researchers calculated the probability of this alignment. If the void and the cold spot were unrelated, the chance of them lining up so precisely was small. Not impossible, but unlikely enough that coincidence seemed improbable. The simplest explanation was that the void caused the cold spot, but the mechanism remained unclear. Standard cosmology predicted that voids should exist. Structure formation naturally creates regions of higher and lower density. Overdense regions collapse into galaxies and clusters. Underdense regions expand into voids. Computer simulations of cosmic evolution routinely produced voids as part of the cosmic web. So finding a void was not surprising. What was surprising was finding one this large. When cosmologists ran simulations starting from the initial density fluctuations measured in the cosmic microwave background, they generated universes filled with structure. These simulated universes contained voids of various sizes. Small voids, a few tens of millions of light-years across, appeared frequently. Medium voids, a few 100 million light-years across, were less common but still expected. Voids approaching 1 billion light-years were rare. The Eridanus Supervoid pushed the boundaries of what simulations predicted. Some studies suggested that a void this large and deep should appear in only about 1 or 2% of simulated universes. That made it a 3 sigma or possibly 4 sigma event in statistical terms. Not impossible, but unusual enough to raise questions. Were the simulations missing something? Was the standard model of cosmology incomplete? Or did we just happen to observe one of the rare universes where such a void formed? These questions could not be answered by finding one void. If the Eridanus Supervoid was unique, it might just be a statistical outlier. But if similar supervoids existed elsewhere, it would suggest they were more common than models predicted. That would indicate a problem with our understanding of structure formation. Astronomers began searching. They looked for other large voids in galaxy surveys and checked whether those voids also aligned with cold spots in the cosmic microwave background. Some correlations appeared. Several other large voids showed weak associations with cooler-than-average regions in the cosmic microwave background. The effect was smaller for those voids, but it was detectable. This suggested the mechanism linking voids to cosmic microwave background temperature was real and repeatable. The searches also revealed that large voids were not as rare as the most pessimistic simulation suggested. The universe contained multiple supervoids approaching or exceeding 1 billion light-years in diameter. The Eridanus Supervoid was among the largest, but it was not alone. This eased some of the statistical tension. If supervoids were more common than early models predicted, it meant those models needed refinement, but it did not mean the standard cosmological framework was broken. Still, the existence of the Eridanus Supervoid demanded explanation. Why did it create a cold spot in the cosmic microwave background? The answer lay in understanding how photons interact with gravitational fields over billions of years of travel. Light does not just pass through space unaffected. Every gravitational potential it encounters changes its energy, subtly but measurably. And when those potentials are themselves changing due to cosmic expansion and dark energy, the effects accumulate. The void was not passively sitting in space, it was expanding, driven by dark energy. This expansion was modifying the gravitational landscape that cosmic microwave background photons traveled through. As photons fell into the void, they gained energy from gravity. As they climbed back out, they lost energy. Normally these effects would cancel perfectly, but the void was growing while the photons were inside it. The exit was easier than the entrance. The photons left with less energy than they arrived with. This energy loss manifested as a temperature decrease. Photons with less energy have longer wavelengths, which corresponds to lower temperature in the blackbody radiation spectrum. The cosmic microwave background photons passing through the Eridanus Supervoid were robbed of energy, arriving at Earth slightly colder than photons that travelled through regions of normal density. The effect was called the integrated Sachs-Wolf effect, named after the physicists who predicted it in 1967. Rainer Sachs and Arthur Wolf calculated that time-varying gravitational potentials would leave imprints on the cosmic microwave background. As the universe evolved and structures grew, the gravitational landscape changed. Photons passing through these changing potentials would gain or lose energy, depending on whether potentials were deepening or shallowing. In dense regions where matter was collapsing into clusters, gravitational potentials deepened over time. Photons passing through these regions gained energy, creating hotspots in the cosmic microwave background. In underdense regions where voids were expanding, gravitational potentials shallowed. Photons lost energy, creating cold spots. The Eridanus Supervoid was the largest and most dramatic example of this effect ever observed. Researchers calculated how much temperature deficit the void should produce. They modelled the void's size, depth, and expansion rate, then traced how cosmic microwave background photons would interact with it. The calculations showed the void could account for roughly half of the observed cold spot temperature deficit. The remaining deficit might come from a combination of the void plus an unlucky primordial fluctuation in the cosmic microwave background itself. The cold spot was likely a hybrid, part ancient, part recent. This explanation satisfied most cosmologists. It required no exotic physics, no collisions with other universes, no topological defects, just standard gravity, cosmic expansion, and a very large void. The Eridanus Supervoid transitioned from mystery to understood phenomenon. Papers were published. The case seemed closed, but the discovery opened new questions. If one supervoid could significantly affect the cosmic microwave background, what else were voids doing to our observations? Were there other large voids along other lines of sight, subtly biasing measurements in ways we had not accounted for? And more troubling, if we lived inside a void ourselves, would we even know? Would our measurements of the universe be systematically distorted without us realizing it? These questions pointed toward an uncomfortable possibility. The Eridanus Supervoid was 3 billion light-years away. We could study it from the outside, map its extent, and model its effects. But there was another void much closer, one that surrounded us completely. And its effects were far more difficult to disentangle from the measurements we use to understand cosmology itself. Gravity does something strange to light. When a photon falls into a gravitational well, it gains energy. Its wavelength shortens, shifting toward the blue end of the spectrum. When it climbs back out, it loses that energy, shifting back toward red. If the gravitational well stays constant, these effects cancel perfectly. The photon exits with exactly the same energy it entered with. This is gravitational redshift, a direct consequence of general relativity, tested and confirmed countless times. But the universe is not static. Gravitational wells change over time, and when they do, the cancellation breaks down. Consider a photon from the cosmic microwave background travelling toward Earth. This photon has been moving through space for 13.8 billion years. During that journey, it passes through structures that did not exist when it started. Galaxy clusters that formed from collapsing overdensities, voids that expanded from underdensities. Each structure has a gravitational potential, a measure of how strongly its gravity affects passing objects. When the photon approaches an overdense region, it falls into that region's gravitational potential and gains energy. If the potential is static, the photon loses exactly that energy climbing back out. No net change. But if matter is still collapsing into the region, the potential is deepening over time. The photon falls into a shallower well than it climbs out of. It exits with more energy than it entered with. The wavelength is shorter, the temperature is higher. The opposite happens in underdense regions. When a photon enters a void, it climbs out of the gravitational influence of surrounding matter. This costs energy. The photon redshifts. When it exits the void, it falls back into the gravitational influence of matter beyond. This returns energy. Normally, these effects balance, but voids are expanding. Dark energy, the mysterious force driving cosmic acceleration, dominates in low-density regions because there is not enough matter to resist it. The void grows larger while the photon is passing through. The gravitational potential becomes shallower. The photon climbs into a deeper potential than it falls out of. It exits with less longer. The temperature is lower. This is the integrated Sachs-Wolf effect. The word integrated means the effect accumulates over the photon's entire path. Every structure the photon passes through contributes. Deepening potentials add energy. Shallowing potentials remove energy. The net result depends on the history of structure formation along that particular line of sight. For the Eridanus Supervoid, the effect is dramatic because the void is so large. A photon entering the void spends hundreds of millions of years traversing it. During that entire time, the void is expanding and its gravitational potential is shallowing. The energy loss accumulates continuously. By the time the photon exits, it has lost a measurable fraction of its energy. Researchers calculated the exact amount. They modelled the void as a spherical underdense region with a 20 to 30% density deficit. They used the standard cosmological model to determine how fast the void should be expanding given its density and the strength of dark energy. Then they traced photon paths through this expanding potential. The result was a temperature deficit of roughly 30 to 40 millionths of a degree Kelvin. The observed cold spot showed a deficit of about 70 millionths of a degree. The void accounted for roughly half. The remaining deficit likely came from a primordial cold fluctuation in the cosmic microwave background itself, an underdense region in the very early universe that happened to align with the void along our line of sight. This combination, primordial fluctuation plus supervoid, explained the observations without requiring new physics. The cold spot was unusual but not impossible. It was a low probability event, the result of two rare things coinciding. The universe had rolled the dice and produced an outlier. But this explanation carried implications. If the Eridanus Supervoid could create such a strong signal in the cosmic microwave background, other voids should create weaker signals. Smaller voids would produce smaller temperature deficits. The cosmic microwave background should be covered in faint cold spots, wherever large voids existed along the line of sight. Similarly, dense regions should produce faint hotspots. Astronomers tested this prediction. They took catalogues of known voids and superclusters from galaxy surveys and compared their positions to the cosmic microwave background temperature map. They stacked the signals from many voids to boost the weak individual effects. The result was clear. On average, voids aligned with cooler than average cosmic microwave background temperatures. Superclusters aligned with warmer than average temperatures. The correlation was weak but statistically significant. This confirmed the integrated Sachs-Wolf effect was real and operating across the entire sky. Voids were draining energy from cosmic microwave background photons everywhere, not just in the direction of the Eridanus Supervoid. The effect was usually too small to notice for any individual void, but it was always present. The confirmation had a deeper consequence. It meant the cosmic microwave background temperature map did not purely reflect the early universe. It also reflected structures that formed billions of years later. Every cold spot and hot spot in the cosmic microwave background was a mixture of primordial fluctuations and integrated Sachs-Wolf contributions. Disentangling these components required knowing the three-dimensional distribution of matter along every line of sight. This was impossible to measure perfectly, which meant some uncertainty would always remain in cosmic microwave background analysis. For most purposes, the integrated Sachs-Wolf effect was a small correction. Primordial fluctuations dominated the cosmic microwave background signal, but for precision cosmology, small corrections mattered. The effect had to be modelled and accounted for. Researchers developed techniques to estimate the integrated Sachs-Wolf contribution and subtract it from cosmic microwave background measurements. This improved estimates of cosmological parameters like the density of matter and the strength of dark energy. The Eridanus Supervoid became a test case. It was the largest known void, producing the strongest integrated Sachs-Wolf signal. If models could accurately predict its temperature signature, they could be trusted for smaller voids. Researchers compared predictions to observations and found good agreement. The models worked. The physics was understood. Yet something nagged at cosmologists. The integrated Sachs-Wolf effect required dark energy. Without dark energy, voids would not expand fast enough to create the observed temperature deficits. The effect was direct evidence that dark energy existed and was causing cosmic acceleration. This was valuable confirmation of a cornerstone of modern cosmology, but it also meant voids were probes of dark energy. Their expansion rates depended on how strong dark energy was. If dark energy varied in strength over time or space, void expansion would vary accordingly. The integrated Sachs-Wolf signal would change. By measuring temperature deficits from voids at different distances, which corresponded to different times in cosmic history, astronomers could test whether dark energy was constant or evolving. Early results suggested dark energy was constant, consistent with it being a cosmological constant, an unchanging energy density built into spacetime itself. But the measurements were not yet precise enough to rule out slow evolution. Future surveys mapping millions of galaxies and characterizing thousands of voids would improve constraints dramatically. The Eridanus Supervoid also raised a question about symmetry. The void created a cold spot by draining energy from photons. But where did that energy go? Energy is conserved. Photons cannot simply lose energy into nothing. The answer was that the energy went into the expansion of space itself. As the void expanded, it did work against the photons passing through it. That work came from the photon's energy. The universe's expansion was literally powered in part by stealing energy from light. This was not unique to voids. All cosmic expansion involved this energy transfer. Photons redshifted as space expanded, losing energy continuously. That energy drove the expansion. It was a closed loop, a consequence of general relativity's equations governing how matter, energy, and spacetime interacted. But voids made the process visible. In dense regions, multiple effects competed and cancelled partially. In voids, the expansion effect dominated cleanly. The Eridanus Supervoid was a natural laboratory, where cosmic expansion's impact on light could be isolated and measured. It was a window into the mechanics of how the universe grew. The void also demonstrated the power of combining different observations. The cosmic microwave background cold spot alone was a mystery. Galaxy surveys alone showed an underdense region, but did not explain why it mattered. Only by combining both datasets did the full picture emerge. The void caused the cold spot through the integrated Sachs-Wolf effect. Two independent measurements confirmed each other and revealed a physical process in action. This synergy between observations was becoming increasingly important in cosmology. No single measurement could answer all questions, but multiple measurements, each constraining different aspects of the same phenomena, could break degeneracies and reveal truth. The Eridanus Supervoid was an example of this principle in action. It showed that the universe could be understood, even when individual pieces of evidence seemed contradictory or incomplete. Yet the void's existence still bothered some researchers, not because the physics was unclear, but because the statistics were uncomfortable. A void this large should be rare. Finding one so perfectly aligned with a cosmic microwave background anomaly seemed too convenient. Perhaps it was just luck, or perhaps the universe contained more large voids than simulations predicted, which would indicate something missing in the models. The answer required finding more supervoids and checking whether they were truly rare or more common than expected. Surveys were underway. Every new galaxy catalogue added data. Slowly, the census of cosmic voids was growing, and with it, the realization that the universe was far more hollow than anyone had imagined. The Eridanus Supervoid was not an isolated freak, it was a member of a population, and that population was beginning to reveal uncomfortable truths about the cosmos we inhabited. The universe is not filled with galaxies. This is the first illusion that breaks when you map cosmic structure in 3 dimensions. Pictures of the night sky show stars everywhere, and deep telescope images reveal galaxies in every direction. The impression is one of fullness, a cosmos packed with matter. The reality is the opposite. When astronomers compile galaxy surveys and plot positions in 3-dimensional space, a pattern emerges that looks nothing like a uniform distribution. Galaxies cluster along thin filaments, like beads on cosmic strings. These filaments connect at nodes where hundreds or thousands of galaxies pile together into clusters. The filaments and nodes form walls, vast sheets where galaxy density is high, and surrounding all of this structure, taking up most of the volume, are the voids. Voids are not small gaps between galaxies. They're colossal regions hundreds of millions of light-years across, where galaxies are rare or absent. A single void can be larger than 1,000 Milky Way galaxies laid end to end. Flying through a void at the speed of light would take hundreds of millions of years. During that entire journey, you would see almost nothing, an occasional faint dwarf galaxy, isolated and alone, mostly just darkness. Measurements from galaxy surveys show that voids occupy roughly 90% of the universe's volume. Filaments, walls, and clusters occupy the remaining 10% but contain most of the mass. This is the cosmic web, and it defines the universe's large-scale structure. Matter is not spread evenly. It is concentrated into a small fraction of space, leaving the rest nearly empty. This distribution is the result of structure formation over billions of years. In the beginning, just after the Big Bang, matter was almost perfectly uniform. Almost, but not quite. Quantum fluctuations during the universe's first moments created tiny variations in density. Some regions were slightly denser than average, others were slightly less dense. The differences were minuscule, about 1 part in 100,000. But gravity amplifies small advantages. Denser regions had slightly more mass, so they pulled more strongly on surrounding matter. This made them denser still, which increased their gravitational pull further. The process fed on itself. Over millions of years, overdense regions collapsed into the first structures. Small clumps of dark matter formed first, because dark matter does not interact with radiation, and could collapse earlier. Normal matter followed, falling into the dark matter clumps and eventually forming stars and galaxies. Meanwhile, underdense regions lost matter to their denser neighbours. As material drained away toward collapsing structures, the underdense regions became emptier. They expanded faster than the cosmic average because there was less gravity to resist the expansion. This created voids. The voids grew over time, pushing their boundaries outward and evacuating more material into the surrounding filaments. Computer simulations of this process reproduce the cosmic web in remarkable detail. Researchers start with initial conditions matching the density fluctuations observed in the cosmic microwave background. They let gravity and expansion evolve the distribution forward in time. Within a few billion years of simulated time, filaments and voids appear. By the present day, the simulated universe looks strikingly similar to the real one. Galaxies cluster along filaments. Voids occupy most of the volume. The cosmic web emerges naturally from the initial conditions and the laws of physics. The simulations also reveal how voids evolve. In the early universe, voids were smaller and less empty. Matter had not yet fully drained into filaments. As time passed, voids expanded and deepened. The process accelerated when dark energy became dominant, roughly 5 billion years ago. Dark energy opposes gravity, adding a repulsive pressure that speeds up expansion. In dense regions, gravity is strong enough to overcome dark energy and hold structures together. In voids, gravity is weak. Dark energy wins decisively. Voids began expanding faster once dark energy took over. This means voids are growing. The Eridanus Supervoid is larger today than it was 1 billion years ago, and will be larger still 1 billion years from now. Its boundaries are pushing outward, eating into the filaments around it. Galaxies near the void's edge are accelerating away from the void's center, driven by the gravitational pull of denser matter beyond. This outflow is measurable. Astronomers can detect it by measuring galaxy velocities and comparing them to expectations from pure cosmic expansion. The void's growth has consequences for everything inside it. Dark matter in the void is being stretched thinner as space expands. Dark energy density remains constant because it is a property of space itself, but matter density declines. This shifts the balance of forces. Dark energy becomes increasingly dominant as matter thins out. The void's expansion accelerates over time. Normal matter in voids experiences this acceleration directly. The few galaxies that exist in voids are moving apart faster than galaxies in typical regions. They are not just receding due to cosmic expansion, they are also being pushed outward by the void's peculiar dynamics. This creates a velocity field, a pattern of motion superimposed on the overall expansion. The velocity field extends across the entire void, affecting everything within it. For the Eridanus Supervoid, this velocity field is substantial. Galaxies in the void's interior are moving outward at speeds of several hundred kilometers per second relative to what cosmic expansion alone would predict. This motion is not random. It is coherent, organized, pointing away from the void's center toward the denser regions beyond its edges. The pattern is exactly what you would expect from an expanding underdensity in a gravitational landscape. Measuring these velocities is difficult because it requires separating the peculiar velocity from the cosmological redshift. Redshift measurements give the total velocity, the sum of recession due to expansion plus motion due to local gravity. Disentangling these components requires independent distance estimates that do not rely on redshift. Techniques like the Tully-Fisher relation for spiral galaxies or surface brightness fluctuations for elliptical galaxies provide such estimates. By comparing the distance-based velocity to the redshift-based velocity, astronomers extract the peculiar velocity. Compiling these measurements for many galaxies in and around the Eridanus Supervoid reveals the velocity field. The pattern matches predictions from models of an expanding void. This is independent confirmation that the void exists and is behaving as theory predicts. The void is not just an absence of galaxies, it is a dynamical structure actively reshaping the motion of everything within and around it. The cosmic web structure is not static, it is evolving, driven by the interplay of gravity and dark energy. Filaments are thinning as voids expand. Galaxy clusters at the nodes of the web are growing through mergers and accretion, becoming richer and more massive. The contrast between dense and empty regions is increasing. The universe is becoming more structured over time, not less. This trend will continue into the far future. Dark energy shows no sign of weakening. Its repulsive effect will keep accelerating cosmic expansion. Voids will grow larger and emptier. Filaments will eventually break apart as the galaxies within them spread too far to remain gravitationally connected. Billions of years from now, the cosmic web will be less web-like. Voids will dominate even more completely. Isolated galaxy groups will drift through an increasingly empty cosmos. The Eridanus Supervoid offers a preview of this future. It is one of the largest and emptiest regions currently known, a place where dark energy's dominance is already nearly complete. Studying it reveals what the rest of the universe will eventually become. The void is not an anomaly. It is a harbinger. But voids also pose a challenge to the cosmological principle, the assumption that the universe is homogeneous on large scales. If you average over large enough regions, the principle says, density should be uniform. Every location should look statistically similar to every other location. There should be no special places. Voids like Eridanus test this assumption. A region 1 billion light-years across is not small. It is a significant fraction of the observable universe's radius. If such structures are common, the universe might be less homogeneous than the cosmological principle requires. If they are rare, we need to explain why we observe one so prominently. The question comes down to statistics. How many large voids should exist in a universe governed by standard cosmology? Computer simulations give an answer, but it depends on the initial conditions and the parameters of the cosmological model. Different simulations produce different numbers of large voids. Some models predict the Eridanus Supervoid is a rare outlier, others predict it is unusual but not impossible. Observations are beginning to settle the question. As galaxy surveys map larger volumes, the census of voids grows. Researchers have identified dozens of large voids, some approaching the size of Eridanus. The voids are not evenly distributed, but they are not vanishingly rare either. The universe appears to produce large voids more frequently than the most conservative models predicted. This suggests the standard model might need adjustment. Perhaps initial density fluctuations had more power on large scales than currently assumed. Or perhaps structure formation is more efficient at creating extreme structures than simulations capture. Either way, the existence of multiple supervoids indicates the universe is more inhomogeneous than early models suggested. The Eridanus Supervoid sits within this larger context. It is one of the most extreme examples of a common phenomenon. Voids are everywhere. They define the universe's architecture, and they are growing, reshaping the cosmos from within. The void is not an isolated curiosity. It is part of a network of emptiness that permeates all of space. Understanding one void means understanding the structure that governs the universe's evolution, and that structure is far stranger than the smooth, uniform cosmos that simple models predict. Standard cosmology has a prediction problem. The lambda cold dark matter model, the framework that explains almost everything we observe about the universe, struggles with the Eridanus Supervoid. Not because the void cannot exist within the model, but because it should be extraordinarily rare. And when something extraordinarily rare shows up prominently in our observations, it forces uncomfortable questions. The model works like this. After the Big Bang, quantum fluctuations created density variations. These variations followed a statistical distribution called a power spectrum, which describes how much fluctuation exists at each scale. Small scales had more power, meaning stronger fluctuations. Large scales had less power. This distribution is measured directly from the cosmic microwave background and forms the starting point for all structure formation. Gravity amplifies these fluctuations over time. Small, strong fluctuations collapse quickly into galaxies. Large, weak fluctuations take longer and produce structures like superclusters and voids. The power spectrum determines how common structures of each size should be. Abundant small galaxies, fewer large clusters, very few extremely large structures. Computer simulations implement this process. Researchers create a virtual universe, seed it with density fluctuations matching the observed power spectrum, and let physics run forward. The simulations use known laws of gravity, the measured amount of dark matter and dark energy, and the expansion history of the universe. The output is a prediction of what structures should exist today. When cosmologists run thousands of these simulations, they generate a distribution of possible outcomes. Most simulated universes look similar. They contain cosmic webs with filaments, clusters, and voids of typical sizes. Occasionally, a simulation produces something unusual, a particularly large void, or an exceptionally rich supercluster. These outliers are rare but not impossible. The Eridanus Supervoid falls into the outlier category. Its size and depth place it in the tail of the distribution. Depending on exactly how you measure the void's properties and which simulation parameters you use, the probability of finding such a void ranges from about 1% to 5%. That means in 100 simulated universes you might find one or a few with a void this extreme. 1 to 5% does not sound impossible, but it is uncomfortable. Science relies on observations being typical, not exceptional. When you observe something that should only appear in 1 out of 20 universes, you start wondering whether your model is wrong or whether you got unlucky. The situation worsens when you account for observational bias. The Eridanus Supervoid is not hidden in some distant, poorly observed region. It sits along a line of sight we have studied intensely because of the cosmic microwave background cold spot. We noticed the cold spot first, then looked for an explanation and found the void. This is not a blind survey where we randomly discovered a rare structure. We went looking for something unusual and found it. This selection effect makes the statistical argument more complex. If you search specifically for anomalies, you will find them. The question is whether the anomaly you find is consistent with random chance, or whether it indicates something deeper. For the Eridanus Supervoid, the jury is still out. Some researchers argue the void is within the bounds of statistical possibility. Others argue it pushes those bounds uncomfortably far. The debate intensifies when you consider that Eridanus is not the only large void. The KBC void, the underdensity surrounding the Milky Way, is even larger at roughly 2 billion light-years across. Other supervoids have been identified in galaxy surveys. The Butter's void, discovered in 1981, is about 330 million light-years in diameter, with an extreme central density deficit. The giant void in the constellation Canes Venatici spans roughly 1.3 billion light-years. Each individual void might be a statistical outlier, but finding multiple outliers starts to look like a pattern. If large voids are supposed to be rare, why do we keep finding them? Either we're observing an unrepresentative sample of the universe, or large voids are more common than the standard model predicts. One resolution is that the initial power spectrum has. The cosmic microwave background measures this spectrum at the surface of last scattering, when the universe was 380,000 years old. but extracting the power spectrum from cosmic microwave background data requires modelling foreground contamination, instrument noise, and the physics of how density fluctuations imprint themselves on the radiation. Small errors in this modelling could lead to underestimates of large-scale power. If the true power spectrum has more fluctuation on scales, structure formation would produce larger voids and richer superclusters more frequently. The extreme structures we observe would become statistically expected rather than rare. This would preserve the standard model's framework while adjusting one input parameter. Testing this hypothesis requires better measurements of the power spectrum. The Planck satellite provided the most precise cosmic microwave background data to date, but even Planck has limitations at the larger scales. Future missions or ground-based experiments with improved sensitivity might reveal additional large-scale power. If they do, the supervoid problem disappears. If they do not, the tension remains. Another possibility is that structure formation is more efficient than simulations capture. The simulations use approximations to handle the enormous computational challenge of modelling billions of particles over billions of years. These approximations might miss subtle effects that enhance the growth of large structures. For example, the simulations often treat dark energy as perfectly uniform. If dark energy has small spatial variations, those could affect how voids expand and deepen. Similarly, the simulations assume general relativity is correct on all scales. If gravity is slightly stronger on very large scales, as some modified gravity theories propose, structures would form more vigorously. Voids would become deeper, superclusters would become richer, the universe would be more inhomogeneous than standard simulations predict. This would explain the abundance of extreme structures without requiring changes to the initial conditions. Modified gravity theories face challenges of their own. They must explain not just large-scale structure, but also the cosmic microwave background, the expansion history, and local tests of gravity like planetary orbits and gravitational wave observations. Constructing a theory that succeeds on all fronts is difficult. Most proposed modifications fail at least one test, but the existence of large voids like Eridanus provides motivation to keep searching for alternatives. A darker interpretation is that the cosmological principle itself is wrong. Perhaps the universe is not homogeneous on large scales. Perhaps structure continues to larger and larger sizes without ever averaging out to uniformity. If this is true, our observations are biased by our location. We see a particular region with particular properties. Other regions might look completely different. This interpretation is philosophically troubling. It means we cannot extrapolate our local observations to the universe as a whole. Cosmology as a science becomes much harder if every region is unique. The predictive power of models collapses. We would be reduced to describing our local patch of space without understanding the global structure. Most cosmologists resist this interpretation. The cosmic microwave background appears highly uniform across the sky, suggesting the universe was homogeneous in the early stages. Large-scale galaxy surveys show similar structure in different directions, consistent with statistical homogeneity. Abandoning the cosmological principle seems premature when simpler explanations like adjusted power spectra or modified gravity remain viable. But the Eridanus Supervoid keeps nagging at the edges of these debates. It exists, it is measured, it is larger and deeper than comfortable, and it is not alone. The universe contains structures that test the limits of what standard models predict. Whether these structures represent rare but allowed fluctuations or evidence of missing physics depends on how the next generation of observations unfolds. Upcoming surveys will map the universe to unprecedented depth and volume. The dark energy spectroscopic instrument is measuring redshifts for tens of millions of galaxies, creating the most detailed three-dimensional map ever produced. The Vera Rubin Observatory will image billions of galaxies, tracing structure across half the observable universe. The Euclid Space Telescope is mapping galaxy distributions and measuring cosmic expansion with exquisite precision. These surveys will discover thousands of voids. The statistical distribution of void sizes and depths will become clear. If large voids are truly rare, the surveys will find only a handful. If they are more common than models predict, dozens or hundreds will appear. The data will settle whether the Eridanus Supervoid is an unlikely outlier or the tip of an iceberg indicating deeper problems with cosmology. Until then, the void remains a puzzle. It fits within the standard model barely. It is allowed by the statistics, just barely. And it suggests that the universe is more extreme, more inhomogeneous, and more surprising than our best models comfortably predict. The void is not breaking cosmology, but it is bending it, testing its limits, and revealing cracks in the foundation that future observations will either widen or seal. Gravity inside a void does not pull inward. This violates intuition, but the geometry demands it. Imagine standing in a valley surrounded by mountains. Gravity pulls you toward the mountains, not toward the valley floor. The mass is in the mountains. The valley is empty. You accelerate toward where the matter is, away from where it is not. Cosmic voids work the same way. All the matter sits outside the void, concentrated in the surrounding filaments and clusters. Inside the void, matter is sparse. A galaxy sitting in the void's interior feels gravitational attraction from all the dense structures beyond the void's boundaries. Those forces do not cancel. They add up, pulling the galaxy outward, away from the void's center. This creates an outflow. Galaxies accelerate away from underdense regions toward overdense regions. The effect is strongest near the void's center, where the density contrast is greatest. It weakens toward the edges where density approaches the cosmic average. But across the entire void, the net motion is outward. For the Eridanus Supervoid, this outflow is measurable. Astronomers have catalogued galaxies within and around the void and measured their velocities using redshift surveys. The velocities show a clear pattern. Galaxies in the void's interior are moving away from the center faster than cosmic expansion alone would predict. The excess velocity, the peculiar velocity, ranges from 100 to several hundred kilometers per second depending on the galaxy's position. This might sound small compared to the speed of light, but it is enormous compared to typical galaxy motions. A galaxy's random motion due to local gravitational interactions is usually tens of kilometers per second. The void-induced outflow is an order of magnitude larger. It dominates the local velocity field. The outflow affects observations in multiple ways. When astronomers measure a galaxy's redshift, they are measuring the total velocity, the sum of cosmic expansion plus peculiar motion. If the galaxy is moving away from us due to the void outflow, its redshift is higher than it would be from expansion alone. This makes the galaxy appear farther away than it actually is. Distance estimates become biased. For individual galaxies, this bias is small and within measurement uncertainties. But for statistical studies involving many galaxies, the bias accumulates. If you are trying to measure the cosmic expansion rate using galaxies in a void, the outflow systematically inflates your result. You measure expansion plus outflow and mistake it for pure expansion. This is not a hypothetical concern. The KBC void, the large underdensity surrounding the Milky Way, creates exactly this problem. Measurements of the Hubble constant using nearby supernovae give higher values than measurements using the cosmic microwave background. The discrepancy is known as the Hubble tension, and it has reached crisis levels in cosmology. One proposed explanation is that we are measuring from inside a void, and the outflow is biasing our local measurements. The Eridanus Supervoid provides a test case. It is far enough away that we observe it from the outside. We can measure the outflow without being embedded in it. The measured velocities match predictions from models of an expanding underdensity. This confirms the physics is correct and the outflow is real. But confirming the outflow exists does not immediately solve the Hubble tension. The KBC void is different from Eridanus. It surrounds us completely. We cannot step outside it to measure its properties objectively. Every measurement we make is potentially contaminated by the void's velocity field. Correcting for this contamination requires modelling the void's size, shape, depth, and velocity profile. All of these are uncertain. The outflow also affects bulk flow measurements. Bulk flow refers to the average velocity of galaxies over large volumes. In a perfectly homogeneous universe, bulk flows should be small and random. Different regions should move in different directions, and when you average over large enough volumes, the net flow should approach zero. Observations show something different. Measurements extending to distances of several hundred million light-years reveal coherent bulk flows with velocities of several hundred kilometers per second. Entire regions of space are moving in the same direction, as if being pulled towards some distant attractor or pushed away from some distant void. The Eridanus Supervoid contributes to these flows. Its outflow extends beyond its boundaries, affecting galaxies in the surrounding regions. The void acts like a repeller, pushing nearby matter away. Combined with attractors like massive superclusters, this creates a complex velocity field with flows in multiple directions depending on location, Mapping these flows requires precise distance measurements for thousands of galaxies. The Cosmic Flows project has compiled the largest such dataset, using techniques like Tully-Fisher and fundamental plane relations to estimate distances independent of redshift. The resulting velocity maps show streams and currents of galaxies flowing through space, driven by the gravitational landscape of voids and clusters. The flows reveal the universe's hidden structure. Galaxy surveys show where matter is, but velocity measurements show where matter is going and what forces are acting on it. Voids appear as sources of outflow, regions where galaxies are accelerating away. Superclusters appear as sinks, regions where galaxies are falling inward. The combination paints a dynamic picture of a universe in motion, constantly rearranging itself under gravity's influence. The outflow from voids has another consequence. It affects the rate at which voids grow. As galaxies accelerate outward, they carry matter with them. This evacuates the void more quickly, deepening the underdensity. The void becomes emptier, which strengthens the gravitational gradient, which accelerates the outflow further. The process is self-reinforcing. Dark energy accelerates this cycle. In a universe without dark energy, gravity would eventually slow the outflow and halt the void's expansion. Matter would stop draining away. The void would reach an equilibrium size. But dark energy provides a repulsive pressure that opposes gravity. In low-density regions like voids, dark energy dominates. It keeps the expansion going indefinitely. Voids never stop growing. This means the outflow will continue into the future. Galaxies currently near the void's edge will eventually be pushed farther out. The void's boundaries will expand. The interior will become even emptier. The Eridanus Supervoid is not a static structure. It is actively evolving, draining matter from its interior and expanding into the surrounding space. The expansion rate depends on the void's density and the strength of dark energy. Deeper voids expand faster because the gravitational gradient is steeper. Stronger dark energy accelerates expansion because it provides more repulsive pressure. By measuring how fast voids like Eridanus are expanding, astronomers can constrain dark energy's properties. Early measurements suggest the expansion matches predictions from the standard cosmological constant model of dark energy. The void is expanding at the rate expected if dark energy has constant density and does not vary over time or space. This is reassuring because it confirms our understanding of dark energy, at least in this context. But the measurements are not yet precise enough to rule out small variations. If dark energy is slightly stronger in voids than in dense regions, or if it was different in the past, the expansion rate would differ from predictions. Future observations with better sensitivity will test these possibilities. The outflow also creates an asymmetry in structure formation. Galaxies near void edges experience competing forces. The void pushes them outward. Nearby filaments pull them inward. The balance determines whether a galaxy falls into a filament or escapes into the void. Most galaxies near void boundaries end up in filaments because the filaments are denser and exert stronger gravity. But some galaxies get stranded in the void, isolated from the main structures. These void galaxies evolve differently from galaxies in dense environments. They experience fewer mergers because neighbours are rare. They retain their gas longer because there is no hot intracluster medium to strip it away. Star formation proceeds slowly but steadily. The galaxies remain blue and star-forming rather than becoming red and dead like cluster galaxies. The outflow ensures these void galaxies stay isolated. As the void expands, the galaxies move farther apart. Interactions become even rarer. Each galaxy becomes an island, evolving in solitude. This creates a population of galaxies that are fundamentally different from the majority. They are cosmological relics, preserved in an environment where the usual forces shaping galaxy evolution are absent. Studying void galaxies provides insight into how galaxies would evolve without external disturbances. It is a controlled experiment, isolating the effects of internal processes like star formation and supernova feedback from external processes like mergers and tidal stripping. The Eridanus Supervoid, with its large volume and well-measured properties, contains a sample of such galaxies. Observing them reveals the baseline of galaxy evolution against which denser environments can be compared. The outflow is not uniform, it varies with position within the void. Near the centre, where density is lowest, the outflow is strongest. Toward the edges, where density rises, the outflow weakens. This creates a velocity gradient across the void. Galaxies at different positions move at different speeds. The pattern is predictable and can be modelled, but it adds complexity to interpreting observations. The Eridanus Supervoid's outflow connects to a broader realization. The universe is not expanding uniformly. Cosmic expansion is the average, but local variations are significant. Voids expand faster than average. Dense regions expand slower or not at all. This patchwork of expansion rates creates a complex velocity field that pervades the entire universe. Every measurement of cosmic expansion is, to some degree, a local measurement influenced by nearby structure. This realization is humbling. It means we cannot measure the universe's true expansion rate from our location alone. We need to account for local effects, correct for nearby voids and clusters, and extrapolate to what the expansion would be in a perfectly average region. The Eridanus Supervoid reminds us that no such average region exists nearby. We are embedded in structure, and structure distorts everything we see. 3 astronomers were counting galaxies when they noticed we were missing several thousand. Ryan Keenan, Amy Barger, and Lennox Cowie published their findings in 2013. The analysis was straightforward. They examined galaxy surveys covering billions of light-years around the Milky Way and compared the observed galaxy density to the cosmic average. The numbers did not match. In every direction, out to distances of roughly 1 billion light-years, there were fewer galaxies than there should be. Not slightly fewer, 20% fewer. The deficit was consistent across multiple surveys and observational methods. It was not an artifact of how galaxies were detected or classified. It was real. The team calculated the statistical significance. A 20% underdensity over such a large volume is rare. Computer simulations of structure formation produce such voids in less than 1% of cases. The probability that we happen to live near the centre of one is correspondingly low, yet the data were clear. The Milky Way sits inside a cosmic void roughly 2 billion light-years across. They named it the KBC void using their initials. The designation sounded casual, almost dismissive for such a profound discovery, but the name stuck. Within cosmology, the KBC void became shorthand for a problem that would not go away. We are not observing the universe from a typical location. We are observing it from inside one of the largest underdensities ever measured. The discovery explained several anomalies that had been accumulating for years. The Hubble constant, the number describing how fast the universe expands, had been measured using 2 independent methods. Observations of the cosmic microwave background gave a value of about 67 km per second per megaparsec. Observations of nearby supernovae gave a value of about 73. The discrepancy was 9%, far larger than the measurement uncertainties. Both groups had checked their work repeatedly. Both were confident in their results. The numbers simply disagreed. The KBC void offered an explanation. If we live inside a large underdensity, the outflow from the void adds to the apparent expansion rate. Nearby supernovae, the ones used for local measurements, are all within the void. Their velocities include both cosmic expansion and the void's outflow. We measure the sum and mistake it for pure expansion. The result is an inflated Hubble constant. Meanwhile, the cosmic microwave background measurement is not affected by local structure. It probes the universe's expansion history averaged over the entire observable cosmos. The cosmic microwave background gives the true global expansion rate. The supernova measurement gives the local rate boosted by the void. The discrepancy is not a measurement error. It is a real difference between local and global expansion. This resolution was elegant. It required no new physics, no modifications to general relativity, no exotic dark energy properties. Just the recognition that our location is unusual. The void's outflow of several hundred kilometers per second could easily account for the 9% discrepancy in Hubble constant measurements. Problem solved. Except the cosmology community did not accept this solution immediately. The reason was philosophical. The cosmological principle states that the universe is homogeneous and isotropic on large scales. No location is special. Every observer, regardless of where they are, should measure the same cosmic properties. If we are in a special location, a statistically rare void that biases our measurements, the cosmological principle is violated. Violations of the cosmological principle make physicists deeply uncomfortable. Science has spent centuries removing Earth from special positions. Copernicus showed Earth is not the centre of the solar system. Hubble showed the Milky Way is not the centre of the universe. The cosmological principle is the ultimate expression of this trend. It says there is no centre at all. every location is equivalent. The KBC void challenges this. If we are in a rare underdensity, we are in a special location by definition. Our measurements are not representative of the universe as a whole. This feels like a step backward, a return to geocentrism. Not literally placing Earth at the centre, but placing it in an unusual environment that affects what we observe. Some researchers proposed alternative explanations for the Hubble tension that did not require a local void. Perhaps dark energy is evolving, changing strength over time, or perhaps there are additional relativistic particles in the early universe that we have not accounted for. Or perhaps systematic errors in supernova distance measurements are larger than estimated. Each alternative preserved the idea that our measurements are typical, and the discrepancy comes from incomplete physics or observational issues. But as more data accumulated, the void explanation became harder to dismiss. Independent studies using different galaxy catalogues confirmed the underdensity. Velocity measurements showed the expected outflow pattern. The void's properties, its size, depth, and shape, were measured with increasing precision. The structure was real, not a statistical fluctuation or observational artifact. The void's size is staggering. 2 billion light-years in diameter means it spans roughly 15% of the observable universe's radius. If you could see the void from outside, it would appear as a vast bubble of darkness, a region where the usual lights of galaxies are dimmed or absent. The Milky Way sits not at the exact centre, but close enough that we are deeply embedded in the underdensity. This position has consequences beyond the Hubble tension. Every cosmological measurement we make is potentially affected. Distance estimates, expansion rates, matter density, dark energy properties, all are derived from observations of objects within or near the void. If the void creates systematic biases, our entire cosmological framework might be skewed. Consider the cosmic distance ladder. Astronomers measure distances to nearby objects using parallax and standard candles. They use those distances to calibrate more distant objects. The process builds outward step by step, each rung relying on the previous one. If the first few rungs are within the void and affected by its outflow, every subsequent measurement inherits the bias. The entire ladder could be systematically wrong. Or consider measurements of the matter density. These rely on counting galaxies and clusters, measuring their masses, and summing the total. If we are in an underdense region, our counts are systematically low. We might underestimate the universe's total matter content. This would throw off calculations of how structure formed and how the universe will evolve in the future. Dark energy measurements are similarly affected. Dark energy's strength is inferred from how fast the universe's expansion is accelerating. But if our local measurements are boosted by the void's outflow, we might overestimate dark energy's effect. The universe might be accelerating slower than we think. This changes predictions for the far future and the ultimate fate of the cosmos. Each of these possibilities is troubling. They suggest that decades of careful observations might be contaminated by a bias we did not know existed. Correcting for the void's influence requires understanding its properties in detail. How large is it exactly? How deep? What is its shape? Is it spherical or elongated? Where exactly is the Milky Way within it? Answering these questions requires mapping the galaxy distribution in 3 dimensions over enormous volumes. Surveys like the Sloan Digital Sky Survey and the 2-degree field galaxy redshift survey have provided much of this data. But gaps remain, especially at large distances where galaxies are faint and hard to observe. The void's boundaries are not sharply defined. Density gradually transitions from underdense to average over hundreds of millions of light-years. Determining where the void ends and normal structure begins is subjective. Different studies using different methods have measured the void's properties and gotten somewhat different results. Some find a 20% deficit extending out to 1 billion light-years. Others find a 15% deficit extending to 1.5 billion light-years. The discrepancies are within uncertainties, but they matter for calculating how much the void affects measurements. The void's shape is another uncertainty. If it is perfectly spherical, the outflow is symmetric and easier to model. If it is elongated or irregular, the outflow varies with direction. Our measurements would be biased differently depending on which direction we look. Some studies suggest the void is slightly elongated, stretched along one axis. Others find it roughly spherical. The data are not yet precise enough to distinguish conclusively. Despite these uncertainties, the basic picture is clear. We live in a large underdensity. It affects our measurements. The question is how much? Can the void fully explain the Hubble tension, or only part of it? Does it affect other measurements significantly, or are those effects too small to matter? Recent work has focused on quantifying the void's impact. Researchers build models of the void based on observed galaxy distributions. They simulate how light and matter move through the void. They calculate how much the outflow should boost local expansion measurements. The results vary depending on assumptions, but most studies find the void can account for at least half of the Hubble tension, possibly more. This is significant, but not definitive. If the void explains half the discrepancy, something else must explain the other half. Perhaps there are additional systematic errors in observations, or perhaps new physics is needed after all. The void does not solve the problem completely. It shifts it, reducing the tension, but not eliminating it. The discovery of the KBC void also raises a meta-question. If we are in one large void, are there others? The Eridanus Supervoid is another example, though farther away. The Boötes void and others have been known for decades. Large voids might be more common than early models predicted. If so, many observers throughout the universe are in similar situations, embedded in underdensities that bias their measurements. This would mean the cosmological principle holds in a statistical sense. The universe is homogeneous when you average over large enough scales, but on scales of 1 billion light-years, significant inhomogeneities exist. Most observers live in or near such structures. Being in a void is not special because voids are common. What matters is recognizing the bias and correcting for it. Alternatively, if large voids are truly rare, we are unlucky. We happen to live in an unusual location at an unusual time when we have developed the technology to notice. This coincidence seems suspicious. Why would we find ourselves in a rare environment precisely when we're capable of studying cosmology? Some invoke anthropic reasoning, arguing that observers can only exist in certain types of environments, but this explanation is unsatisfying to many. The KBC void is now a central piece of the cosmological puzzle. It cannot be ignored. Every major survey and analysis must account for it. Future missions are designed to map the void's properties with higher precision. The goal is to measure its influence well enough to correct all cosmological measurements and determine the universe's true properties, independent of our local environment. But there is a deeper realization. If the KBC void affects us, and the Eridanus Supervoid affects observations in its direction, voids in general are shaping what we see. The universe we observe is not the universe as it truly is. It is the universe as seen through the distorting lens of structure. Voids, filaments, clusters, all leave their fingerprints on the light and matter passing through them. Cosmology is not just about distant objects. It is about the space between us and them, and that space is far from empty. Dark energy is invisible, unchanging, and comprises 68% of the universe. It is also almost impossible to study directly. Unlike matter, which clumps into galaxies and emits light, dark energy is diffuse and interacts with nothing except space-time itself. It does not emit radiation. It does not absorb radiation. It simply exists, exerting a negative pressure that accelerates cosmic expansion. This makes dark energy frustratingly elusive. Physicists cannot put it in a laboratory. They cannot point a telescope at it. The only way to study dark energy is through its effects on the universe's expansion and structure formation. And the best places to observe those effects are cosmic voids. In dense regions like galaxy clusters, gravity dominates. The cluster's mass pulls galaxies inward, holding the structure together despite cosmic expansion. Dark energy is present, but its effect is overwhelmed by gravity. Measuring dark energy's influence in these environments is like trying to hear a whisper during a thunderstorm. The signal is drowned out. Voids are different. With matter sparse and gravity weak, dark energy takes over. The void expands faster than the cosmic average because there is nothing to resist. Dark energy's repulsive pressure pushes space apart without opposition. This makes voids natural laboratories where dark energy's properties can be isolated and measured. The expansion rate of a void depends on dark energy's strength. If dark energy is stronger, voids expand faster. If it is weaker, they expand slower. By measuring void expansion directly, astronomers can test whether dark energy behaves as theory predicts. The standard model assumes dark energy is a cosmological constant, an unchanging property of empty space with constant density. If this is correct, voids should expand at a specific calculable rate. Observations of the Eridanus Supervoid and other large voids provide this test. Researchers measure the velocities of galaxies within and around voids, looking for the outflow pattern that indicates expansion. They compare the measured expansion rate to predictions from the cosmological constant model. So far, the observations match predictions. Voids are expanding at the expected rate, consistent with dark energy being a true constant. Alternatives. Dark energy could be slowly evolving, changing strength over cosmic time, or it could vary in space, being slightly stronger in some regions and weaker in others. These scenarios are called dynamical dark energy, or inhomogeneous dark energy. They require modifications to the standard model, but remain theoretically possible. Testing for evolution requires observing voids at different distances, which corresponds to different times in cosmic history. A void 3 billion light-years away is seen as it was 3 billion years ago. A void 6 billion light-years away is seen 6 billion years ago. If dark energy was different in the past, void expansion rates should vary with distance. Nearby voids should expand differently from distant voids. Current surveys are beginning to enable this test. Catalogues now include thousands of voids spanning a range of distances. Statistical analyses can compare expansion rates across cosmic time. Early results show no significant variation. Voids at different distances expand at rates consistent with constant dark energy. But the error bars are still large. A slow evolution could be hidden within the uncertainties. Testing for spatial variation requires comparing voids in different directions. If dark energy is stronger in some regions, voids there should expand faster. This would create an asymmetry in the cosmic expansion, violating the assumption of isotropy. Some researchers have searched for such asymmetries and found hints of anomalies, but nothing conclusive. The data remain consistent with uniform dark energy within measurement precision. Void shapes provide another test. If dark energy is perfectly uniform, voids should expand equally in all directions, maintaining spherical shapes as they grow. But if dark energy has structure, spatial variations in its strength, voids might expand more in some directions than others. They would become elongated or distorted. Measuring void shapes and looking for systematic patterns of distortion can reveal whether dark energy has hidden structure. The Eridanus Supervoid appears roughly spherical in current measurements, consistent with uniform dark energy. But the measurements are not precise enough to detect small deviations. Future surveys with better resolution will map void shapes in finer detail. If distortions appear, they would indicate dark energy is more complex than the simple cosmological constant model. Voids also offer insight into dark energy through their gravitational effects. The integrated Sachs-Wolf effect, which creates the cosmic microwave background cold spot, is directly powered by measurable temperature deficits. The strength of the effect depends on how much dark energy is present and how strongly it accelerates expansion. By measuring the temperature deficit from many voids and comparing it to predictions, astronomers can constrain dark energy's equation of state. This is a parameter describing the relationship between dark energy's pressure and density. For a cosmological constant, the equation of state equals -1. Other values indicate dynamical dark energy. Current measurements from the integrated Sachs-Wolf effect are consistent with -1, but again, the uncertainties are large enough that small deviations could be hiding. The importance of voids for dark energy research cannot be overstated. They are the only environments where dark energy's effects are dominant and measurable. Every other method of studying dark energy, whether through supernova distances, cosmic microwave background fluctuations, or gravitational lensing, involves disentangling dark energy's signal from the competing effects of matter and gravity. Voids eliminate that complication. They are clean, simple systems where dark energy runs the show. This makes voids critical for the next generation of cosmological surveys. Missions like the Dark Energy Spectroscopic Instrument, the Vera Rubin Observatory, and the Euclid Space Telescope are all designed to map cosmic structure in unprecedented detail. One of their primary goals is to catalogue thousands of voids, measure their properties, and use them to constrain dark energy. The surveys will measure void sizes, depths, shapes, and expansion rates across a wide range of distances. They will test whether dark energy is constant or evolving, uniform or structured, simple or complex. The answers will determine whether the cosmological constant model is correct or whether new physics is needed. If dark energy is confirmed to be a true cosmological constant, it would be one of the most profound discoveries in physics. It would mean the universe has a built-in acceleration, a fundamental property of space-time itself. Understanding why this property exists and why it has the specific value we measure would become the central question. The cosmological constant problem, the puzzle of why dark energy's density is so small compared to theoretical expectations, would demand an explanation. If dark energy is instead dynamical or inhomogeneous, it would open entirely new avenues of research. Physicists would need to identify what field or mechanism produces the dark energy and why it behaves the way it does. This could connect to theories of quantum fields, extra dimensions, or modifications to gravity. The implications would ripple through all of fundamental physics. Either outcome depends on understanding voids. The Eridanus Supervoid, with its size and proximity, is a key target. It is large enough to produce strong signals and close enough to measure precisely. Observations of its expansion rate, shape, and gravitational effects will provide some of the tightest constraints on dark energy properties. But the Eridanus Supervoid also illustrates a limitation. It is just one void. Cosmic variance, the statistical uncertainty from observing a finite sample, means a single void cannot definitively answer questions about dark energy. Thousands of voids are needed to average out random variations and reveal the underlying physics. This is why large surveys are essential. The future of dark energy research lies in mapping the cosmic web in exhaustive detail. Every void, every filament, every cluster contributes information. The web's structure encodes the history of cosmic expansion and the influence of dark energy over billions of years. Extracting that information requires combining observations across all scales and distances. Voids are not just empty spaces in this picture. They are active participants in cosmic evolution, growing and shaping the universe around them. They are the places where dark energy's influence is strongest and most visible. Understanding them is understanding the force that will determine the universe's ultimate fate. Billions of years from now, dark energy will have driven voids to dominate the universe completely. Filaments will thin and break apart. Galaxy clusters will become isolated islands surrounded by expanding emptiness. The cosmic web will dissolve into a sparse collection of matter, lost in an ocean of accelerating space. Voids will have won. Studying voids today is studying that future. It is understanding the mechanism that is already reshaping the cosmos and will continue doing so forever. Dark energy is not a distant abstraction. It is here, now, in the voids that surround us. The Eridanus Supervoid is a window into this process, a laboratory where the universe's fate is already unfolding, and we are only beginning to learn how to read what it is telling us. The universe is aging into emptiness. This is not metaphor. It is the inevitable consequence of dark energy's dominance. As cosmic expansion accelerates, voids grow faster and filaments thin. The balance of structure is shifting. What we see today, a cosmos rich with galaxies and clusters, is temporary. The true equilibrium state of the universe is void. The process is already underway. The Eridanus Supervoid is expanding at several hundred kilometers per second, driven by dark energy's repulsive pressure. Every year, the void grows larger. Every million years, more matter evacuates from its interior into the surrounding filaments. The void deepens, becoming emptier and darker. This expansion will not stop. There is no mechanism to halt it. Dark energy does not weaken or decay. It remains constant while matter dilutes. In a billion years, the Eridanus Supervoid will be noticeably larger than it is today. Galaxies currently near its edges will have been pushed farther out. The few dwarf galaxies in its interior will be even more isolated, separated by distances too vast for light to cross in reasonable time. The void will have consumed more of the cosmic web, converting structured space into empty space. In 10 billion years, the transformation will be dramatic. Voids will occupy an even larger fraction of the universe's volume, approaching 95% or more. Filaments will be stretched thin, barely connected strands of galaxies separated by enormous distances. Galaxy clusters will still exist, but they will be isolated nodes, be less web and more archipelago. In 100 billion years, the structure we observe today will be unrecognizable. Most galaxies will have exhausted their gas and stopped forming stars. The universe will dim as stellar populations age and die. Red dwarfs, the longest-lived stars, will dominate, but even they will eventually fade. The galaxies that remain will be collections of dead stellar remnants. White dwarfs, neutron stars and black holes drifting through darkness. Voids will have expanded so much that galaxies within them will lose causal contact with each other. The space between them will be expanding faster than light can cross. A galaxy in the interior of a void will see its sky empty except for the few members of its local group, gravitationally bound companions that resist cosmic expansion. Everything else will have receded beyond the cosmic horizon, the boundary beyond which light cannot reach an observer before the universe expands too much. This isolation is already beginning for observers in the largest voids. A civilization arising in a void galaxy a few billion years from now will see a dramatically emptier sky than we do. The cosmic microwave background will be redshifted to undetectable wavelengths. Distant galaxies will have faded from view. The evidence for the Big Bang, for cosmic expansion, for the existence of a universe beyond the local group will be gone. Such a civilization might conclude they live in a small, static island universe, surrounded by infinite empty space, never suspecting the vaster cosmos beyond their horizon. This scenario, sometimes called the dark future, is cosmology's version of heat death. Not a dramatic collapse or explosion, but a slow fading into isolation and darkness. The universe does not end. It simply becomes empty, cold, and unreachable. Each remaining structure is alone, drifting through an expanding void with no hope of contact or discovery. For observers in the KBC void, this future is closer than for those in denser regions. We're already in an underdensity. Our sky is already emptier than average. The Milky Way and Andromeda will merge in about 4 billion years, forming a single large galaxy. This merged galaxy, sometimes called Milkomeda, will be the dominant structure in the local group, but the local group itself will become increasingly isolated. The Virgo cluster, currently about 50 million light-years away, will recede beyond reach within tens of billions of years. The galaxies of the local sheet, the structure containing the Milky Way and nearby groups, will spread apart as the KBC void expands. Eventually, Milkomeda will be alone, surrounded by darkness. Future astronomers in that galaxy will have no way to observe the cosmic microwave background, no distant galaxies to measure expansion, no evidence of structure beyond their immediate vicinity. They will face a cosmological crisis. Without external references, they cannot test theories of the universe's origin or evolution. They cannot measure the expansion rate or determine the universe's age. They will be prisoners of their location, unable to see beyond the void that surrounds them. Cosmology as a science will be impossible. This raises an uncomfortable question. Are we in a similar situation now? The KBC void affects our measurements. The Eridanus Supervoid distorts observations in its direction. How many other voids exist along other lines of sight, subtly biasing what we see? Are we already cosmological prisoners, observing a distorted version of the universe without realizing it? The answer depends on how well we can map and correct for local structure. If we can measure the distribution of matter accurately enough, we can model its effects and subtract them from observations. This is possible in principle, but it requires data we do not yet have. Future surveys will help, but there will always be uncertainties. We can never be completely certain we have accounted for all biases. The long-term fate of voids is also a question about dark energy's nature. If dark energy is truly a cosmological constant, its density remains unchanged as the universe expands. But matter and radiation dilute. Eventually, dark energy will be the only significant component of the universe's energy budget. It will dominate completely, driving exponential expansion. In this scenario, voids expand forever. The universe becomes a de Sitter space, an exponentially expanding void with no structure except isolated pockets of matter that have not yet evaporated through quantum processes. This is the ultimate destiny if dark energy is constant. But if dark energy evolves, the future could be different. If dark energy weakens over time, expansion will slow. Voids will stop growing. The universe might even reach a maximum size and begin contracting, leading to a big crunch. If dark energy strengthens, expansion will accelerate faster, potentially tearing apart galaxies, stars, and eventually atoms in a big rip. The fate of voids depends entirely on dark energy's behavior. Current observations favor the constant dark energy scenario. Voids are expanding at rates consistent with a cosmological constant. No evidence of evolution has been detected, but the measurements span only a fraction of cosmic history. Extrapolating billions of years into the future based on a few billion years of data is risky. dark energy could change in ways we have not yet observed. The study of voids is therefore a study of cosmic destiny. By measuring how voids grow and evolve, astronomers are measuring the force that will shape the universe's far future. The Eridanus Supervoid, the KBC Void, and all the other large voids are laboratories where this future is already being written. They are not distant curiosities. They are previews of what the entire universe will become. This realization is humbling. The universe we observe, with its galaxies and clusters and rich structure, is a transient phase. The true nature of the cosmos is emptiness. Structure is the anomaly, a brief flowering in a universe that will spend most of its existence as void. We live in a special time, a cosmic spring when structure still exists and can be observed. Future eras will be a long winter of isolation and darkness. But even this bleak picture contains possibility. If civilizations survive long enough, they will adapt to the changing cosmos. They will learn to generate energy from sources other than stars. They will engineer structures that resist the pull of cosmic expansion. They might even find ways to communicate across expanding space, bridging the voids that separate them. Or they might not. The universe does not care whether life survives. Dark energy will continue accelerating expansion, regardless of what intelligent beings wish. Voids will grow, structure will dissolve, the cosmos will empty. This is not a moral judgment or a tragedy. It is simply physics, playing out over timescales so long that human intuition cannot grasp them. The Eridanus Supervoid is a microcosm of this process. It is a region where the future has arrived early. The void is already doing what the entire universe will eventually do, expanding, emptying, isolating. By studying it, we are studying our own distant fate, and the lesson is clear. The universe is not a place of permanence, it is a place of change, and that change points inexorably toward emptiness. Yet in the present, voids remain tools for discovery. They reveal dark energy's properties, they test the limits of cosmological models, they challenge our assumptions about homogeneity and typicality. They force us to confront uncomfortable questions about our location and whether our measurements can be trusted. The Eridanus Supervoid and the KBC Void are not just features of the cosmic web. They are gateways to understanding the universe's deepest truths. And those truths are stranger and more unsettling than we ever imagined. The questions cosmic voids raise have no clean answers. Every measurement of the Eridanus Supervoid, every analysis of the KBC Void, every simulation of structure formation leads to more uncertainty rather than less. This is not a failure of science. It is the nature of studying phenomena that challenge the foundations of our models. The first unresolved question is statistical. Are supervoids like Eridanus rare outliers or common features we have simply underestimated? Standard cosmology predicts they should be rare, appearing in only 1 to 5% of simulated universes. Yet we observe multiple examples, the KBC void surrounding us, the Eridanus Supervoid 3 billion light-years away, the Buta's void, the giant void in Cain's Venatici. Each one is large enough to push the boundaries of what models comfortably predict. If these structures are genuinely rare, we face an anthropic problem. Why do we find ourselves in a universe and location where rare structures happen to be prominent? Some invoke the weak anthropic principle. Environments and those environments might correlate with unusual large-scale structure. But this explanation feels like giving up, accepting that we cannot understand our observations through fundamental physics alone. If supervoids are common, the models are wrong. Either the initial density fluctuations after the Big Bang features than simulations capture. Both possibilities require adjustments to the standard cosmological framework. Neither is comfortable. The second question concerns modified gravity. Multiple researchers have proposed that gravity behaves differently on cosmological scales than general relativity predicts. Some theories suggest gravity is stronger on large scales, which would enhance structure formation and make large voids more common. Others propose screening mechanisms where gravity's strength depends on local density, becoming effectively stronger in low-density regions like voids. These theories can explain the abundance of large voids without invoking statistical bad luck. They predict that voids should be larger and deeper than standard models allow. The Eridanus Supervoid fits naturally into these frameworks. But modified gravity theories face their own challenges. They must explain not just voids, but also the cosmic microwave background, galaxy rotation curves, gravitational lensing, and the expansion history. Constructing a theory that succeeds everywhere is difficult. Most proposals fail at least one critical test. Testing modified gravity requires precise measurements of how matter moves in voids versus dense regions. If gravity is genuinely different in voids, galaxy velocities should deviate from general relativity's predictions in specific calculable ways. Current measurements are not precise enough to detect these deviations conclusively. Future surveys will provide better data. Within a decade, observations should either confirm general relativity works in voids or reveal anomalies that demand new physics. The third question is about the cosmological principle. This sufficiently large scales. It is a foundational assumption underlying all of cosmology. Without it, the equations simplify and predictions become possible. With violations, cosmology becomes vastly more complicated. The KBC void represents a potential violation, a 2 billion light-year under-density universe. If we are embedded in such a structure, our measurements are not representative of cosmic averages. We are in a special location. This contradicts the spirit of the cosmological principle, even if it does not technically violate the principle's mathematical formulation. Some researchers argue the principle should be revised. Perhaps homogeneity only applies on scales much larger than previously thought, maybe 10 billion light-years or more. This would allow large voids and superclusters to exist without violating the principle. But it would also mean we cannot test homogeneity directly, because we cannot observe volumes large enough to average over the inhomogeneities. We would be assuming homogeneity on faith rather than confirming it through observation. Others argue the principle holds statistically. All locations, even if individual locations vary significantly. By this interpretation, many observers are in voids. This preserves the principle's spirit while acknowledging local variations. The fourth question concerns the Hubble tension. The KBC void offers a partial explanation. Its outflow can account for some of the discrepancy between local and cosmic microwave background measurements of the expansion rate. But recent analyses suggest the void alone cannot explain the entire tension. Even after correcting for the void's effects, a residual discrepancy remains. This means something else is contributing. Possibilities include systematic errors in distance measurements, unaccounted for peculiar velocities from structures beyond the KBC void, or genuine new physics in the early universe that affects the cosmic microwave background-derived expansion rate. Each option has supporters and detractors. The debate is unresolved and intensifying as measurements improve. The Hubble tension has reached crisis proportions. Both measurement methods are incredibly precise, with uncertainties of only a few %. The discrepancy is now at the 5 to 6 sigma level, meaning the probability it is due to random chance is less than 1 in a million. Something is wrong. Either the measurements, the models, or both. The KBC void reduces the tension but does not eliminate it. A complete solution remains elusive. The fifth question is about the integrated Sachs-Wolf effect and the cosmic microwave background cold spot. The Eridanus Supervoid accounts for roughly half of the observed temperature deficit. The other half is attributed to a primordial fluctuation, an underdense region in the. This explanation works statistically but feels contrived. Two rare things, a primordial cold fluctuation and a supervoid, perfectly aligned along the same line of sight. The odds are low. Some researchers have proposed alternative explanations. Perhaps the void is larger or deeper than current measurements suggest, which would allow it to explain the entire cold spot without requiring a primordial contribution. Or perhaps the integrated Sachs-Wolf effect is stronger than standard models predict, which would indicate dark energy behaves differently than assumed. Both possibilities require better observations to test. The sixth question is philosophical. If we live in a void that biases our measurements, can we trust anything we think we know about the universe? Every cosmological parameter, from the Hubble constant to the age of the universe to the density of dark matter, is derived from observations made within the KBC void. If those observations are systematically biased, the parameters are wrong. Our entire cosmological framework could be built on a distorted foundation. This is a nightmare scenario for cosmologists. It suggests decades of careful work might need to be revisited and corrected. But it is also an opportunity. If we can measure the void's properties accurately and model its effects, we can correct the bias and extract the true cosmic parameters. This requires better data, better simulations, and better understanding of how structure affects observations. All of these are achievable with current and near-future technology. The seventh question concerns dark energy itself. Voids are the best places to study dark energy, but they also introduce complications. If dark energy varies spatially, being stronger or weaker in different regions, voids might not be representative. Measurements of dark energy in voids might not apply to the universe as a whole. Testing for spatial variation requires comparing many voids in different locations, which demands large surveys. Current data show no evidence of spatial variation. Dark energy appears uniform, but the measurements are not yet sensitive enough to detect small variations. If dark energy varies by 10 or 20% across the observable universe, current surveys would miss it. Future missions will improve sensitivity, but the question will remain open for years. The eighth question is about the universe's age. If the high local Hubble constant is correct, the universe is younger than cosmic microwave background measurements suggest. This creates conflicts with the ages of the oldest stars. Globular clusters appear to be about 13 billion years old, but a younger universe would be only 12.7 billion years old. You cannot have stars older than the universe. The KBC void might resolve this by showing the high local Hubble constant is inflated by the outflow. But uncertainties remain. Stellar ages have their own uncertainties. The void's effects are uncertain. The cosmic microwave background-derived age depends on model assumptions. Every parameter is connected to every other parameter. Changing one affects all the rest. Resolving the age question requires simultaneously resolving the Hubble tension, the void properties, and the stellar evolution models. This is a monumental task. The ninth question is about bulk flows. Observations show that galaxies within several 100 million light-years are moving coherently in organized patterns, with velocities exceeding what standard cosmology predicts. The KBC void and other large structures create these flows through their gravitational influence. But the observed flows are larger than models predict. Either the structures are more massive or more numerous than thought, or gravity works differently on these scales. Measuring bulk flows is difficult because it requires accurate distances to many galaxies. Current measurements have large uncertainties. Future surveys will improve precision, but disentangling the contributions from different structures is challenging. The KBC void, the Shapley supercluster, the Eridanus Supervoid, and other features all contribute to the local velocity field. Isolating each contribution requires detailed modelling and excellent data. The 10th and perhaps most profound question is what voids mean for the ultimate nature of the universe. Are they temporary features that will eventually dissolve as the universe continues evolving? Or are they permanent, growing structures that will dominate the cosmos forever? The answer depends on dark energy's behaviour over timescales of trillions of years, far beyond what we can observe directly. If dark energy is constant, voids are the future. The universe will empty, becoming a collection of isolated structures surrounded by expanding voids. If dark energy evolves or decays, the future could be different. Voids might stop growing or even contract. Structure might reform in currently empty regions. The cosmos could undergo cycles of structure and dissolution. We do not know. What we do know is that voids are not anomalies. They are fundamental features of cosmic structure. They occupy most of the universe's volume. They dominate its dynamics. They affect every measurement we make. Isolated curiosities. They are windows into how the universe works, revealing processes and forces that would be hidden in denser regions. These voids challenge us to rethink basic assumptions. They force us to question whether our location is typical, whether our models are complete, whether our measurements are trustworthy. Every answer leads to more questions. Every solution creates new problems. This is not a failure. This is frontier science, where the boundaries of knowledge are being pushed outward into the unknown. The voids are teaching us humility. We thought we understood the universe's structure. We thought we could measure its properties from any location and get the same answers. We thought the cosmological principle guaranteed our observations were representative. The voids show us we were wrong. Our location matters. Structure matters. The universe is more complex, more inhomogeneous, and more strange than we assumed. But the voids are also teaching us how to do better. They show us what to look for, what to measure, what to correct. They provide natural experiments where dark energy dominates and structure formation is simplified. They are laboratories we could never build, revealing physics we could never test any other way. The Eridanus Supervoid, 1 billion light-years of near-nothingness, is one of the most valuable scientific resources in the observable universe. Use it.